Welcome viewers to the second segment of the fourth lecture for the online series of lectures for the course of General Relativity. Towards the end of the first segment, we were discussing the signature of the metrics, and we were discussing earlier that the signature of the matrix is independent of the choice of the basis for the respective tensor product vector spaces. So now in this lecture we'll first define Riemannian or Lorentzian manifold. So definition: a Riemannian or Lorentzian manifold is a pair M, G, where M is a Riemannian or Lorentzian manifold and G is a Riemannian or a Lorentzian metric tensor field. Alright, so here is an important point on a Riemannian manifold. One can define the length, of a curve as is done naturally in R3, length of a curve as is done in R3. That is, for a curve, we mean a map from the interval AB to the manifold, underlying manifold M. So curve is a smooth map like this, where lambda A, B to M being a smooth curve with tangent vector x at lambda of t. Okay, t taking values in this interval AB. Right now, the length is given by this integral, right? dt G is the metric tensor field that the Riemannian manifold is equipped with, and G at lambda t is the corresponding tensor, and this tensor is going to act on two tangent vectors, both being x at lambda t. Good. And this is nothing but dt G x comma x at lambda t, right, to the 1/2. to the 1/2. I guess I should use a 1/2 here as well. Okay, so I should use a 1/2 here as well. Okay, so all right, in a coordinate basis. So in the coordinate basis, so let me erase everything here. In a coordinate basis, we write. So in the coordinate basis, we write the metric tensor field as g mu del dx mu tensor dx nu. Okay. Now a few examples. The number one example is that of a Euclidean metric, Euclidean space in R to the n, which is the collection of n tuples, x1, x2, all the way up to xn, the collection of all n tuples. It's a vector space actually. The Euclidean metric, the Euclidean metric is given by dx1 tensor dx1 plus all the way up to dxn tensor dxn. Okay. All the off diagonal elements vanish. Okay, and together this pair Rn comma G is called the Euclidean space. So in this case, case of Euclidean space, our coordinate chart covers all of Rn, in which the components of the metric are is this matrix. It's a diagonal matrix with one set at the diagonal. Okay, and such a coordinate chart is called Cartesian. So let me write it for you. A coordinate chart in the Euclidean space. Coordinate chart which covers all of R to the n, and in which the components of the metric, the components of the metric are this diagonal matrix, where one is situated along the diagonals, along the main diagonal, is called Cartesian. Okay, now the second example is that of Minkowski Spacetime that we use in special theory of relativity. In R4, so the underlying space is that of R4, x0, x1, x2, x3. So it's a collection of 4 tuples. The Minkowski metric, is eta minus dx0 tensor dx0 plus dx1 tensor dx1 plus dx2 tensor dx2, and finally dx3 tensor dx3. This Lorentzian manifold is called Minkowski Spacetime. Okay, now our coordinate chart here, in this case, our coordinate chart which covers all of R4, all of R to the 4, and in which coordinate chart, and in which the components of the metric after diagonalization, the components of the metric are eta mu mu, which is 4 times 4 diagonal matrix with -1, +1, +1 and +1 situated along the main diagonal, is called an inertial frame or inertial frame of reference. So inertial frame is a coordinate chart in Minkowski spacetime. Okay, now the third example is that of S2, two-dimensional sphere, a soccer ball. On S2, let theta comma phi denote the spherical polar coordinate chart. The spherical polar coordinate chart then the round metric on S2, the round unit metric to be more precise, on S2 is G equal to d theta tensor d theta plus sine square theta d phi tensor d phi. Okay. In this polar coordinate chart, theta phi, we have G mu nu, the components of the metric is the diagonal matrix 1 sine squared theta. Okay, so let us discuss Lorentzian signature a little in detail now. Okay, so Lorentzian signature. On a Lorentzian manifold, we take basis indices. We take basis indices mu nu to run from 0 to n minus 1. So there can be n values of each of the indices. Okay. starting from 0 to n minus 1. At the point P in M, we choose an orthonormal basis E mu, so that the matrix with entries of the metric components gets this matrix gets diagonalized. This symmetric matrix gets diagonalized. That is, G at P acting on these two basis vectors, E mu at P and E nu at P, should be simply the Minkowski metric. Well, it's a generalization of Minkowski metric, meaning that we have the first one, to be more precise, Lorentzian metric. So the first one being -1, and all the rest of the diagonal entries should be +1. Okay, so there are n-1 positive ones here, and the first one being -1. Okay. Well, now the thing is that such a basis E mu is not unique, right? There can be many such orthonormal bases, which will put this thing into this diagonal form. Okay, such a basis is not unique. Okay, let E prime mu at P be any such basis, any other basis with the following transformation of basis elements. This is A inverse. I'm going to explain in a while what these matrices A are. Okay, bear with me. This is mu, this is nu, and this is going to be evaluated at phi of, I think it should be phi prime of P, and this is E nu at P. Okay, so it's the change of basis formula for us at the point P. Okay, so both of them are orthonormal bases at the tangent space at the point P of the manifold. Okay, let me erase this part. Okay, now recall how basis vectors change under change of charts. I want you to recall how basis vectors of the tangent spaces change under change of charts. Del by del x nu at P is going to be equal to del x prime nu del x mu, and this is going to be evaluated at phi of P, and del by del x prime nu at P. Okay, this is what we have already studied probably in lecture 2 so there are two charts involved. One is phi and the other one is phi prime. For the chart phi, the local coordinates are given by x mu, and for the chart phi prime, the local coordinates are given by x prime mu. So phi prime composed with phi inverse is a map from r to the n to itself, and this matrix is a matrix given by precisely the one that we have here, del x prime mu by del x mu. This is this matrix, right? Phi prime composed with phi inverse, the mu component, and this is going to be our matrix A. Okay, good. So let me write it here. Del x prime mu at P is going to be equal to, so I'm just reversing just writing the prime coordinates using the unprimed coordinates now. Del x mu by del x prime mu, right? And this is going to be evaluated at phi prime of P. Okay, and this is del by del x mu at P. Okay, and we have seen that this guy is phi composed with is the inverse of this guy. Phi composed with phi prime inverse, and the entries are mu nu, right? So this is nothing but A inverse, the matrix A inverse, and the components are mu nu. So in other words, so using the matrix A, we can write the change of basis elements at the respective tangent space as this, right? A inverse mu nu at phi prime P del by del x mu at P. Okay, all right, so this is what's going to happen, right, in the tangent space. So the different orthonormal bases are connected to each other by these matrices, by the entries of the matrices A inverse. Okay, now let me erase this part. Now eta prime mu nu at P is nothing but G at P, and this is going to act on the two basis elements in the prime coordinate system, or in the 5' chart, right? Like this. So using our basis, using the transformation of the basis elements in the tangent space, we know that this is going to be G at P, and this is A inverse mu sigma at phi prime P, E sigma at P, A inverse mu rho at phi prime P, and E rho at P. Okay, so I'm just using this formula here. So from which we see that, so these numbers will come out of this, come out of the bracket. A inverse mu sigma at phi prime P, then I have A inverse mu rho at phi prime P, okay, and then I have G at P acting on E sigma at P, comma E rho at P. Okay, so we at the end have eta prime mu at P going to be equal to A inverse mu sigma at phi prime P, A inverse mu rho at phi prime P, and this guy, this thing is eta sigma rho at P, right? So this is what we have at the end, right? So does it look familiar to you? You ask yourself, recall special theory of relativity, and see that these A's are precisely Lorentz transformations. We abbreviate this as eta prime mu to be A inverse mu sigma, A inverse mu rho eta sigma rho. So we have just seen that different orthonormal bases E mu at P, and the primed ones E nu prime at P in M are related by Lorentz transformations. Of special theory of relativity. The A's are actually nothing but lambdas of STR. This is important. Okay, now we are all set to define Lorentzian manifold. Let me erase everything and give you the definition of Lorentzian manifold. Definition. So we already defined Lorentzian manifold. Now we are going to define space-like, time-like, and light-like vectors on a Lorentzian manifold. On a Lorentzian manifold, M comma G, a non-zero vector x at P in the tangent space TPM is time-like if G at P, x at P, x at P is negative definite. Null or light-like if G at P, xp, xp is equal to 0, and space-like if G at P, x at P, x at P is strictly positive. Okay. So this vector in the tangent space is going to be light-like if this number is 0. This is going to be time-like if the number is strictly negative, and this tangent vector is going to be space-like if this number is strictly positive. Okay. So remark on the definition of space-time manifold. So space-time. So in an orthonormal basis, at P in M, the metric has components atom union, which is like, -1 in the first entry and +1 in the rest of the n-1 entries. Okay. So since this is the case, the tangent space at P has exactly the same structure, as Minkowski spacetime. That is, null vectors at P define a light cone that separates time-like vectors at P from space-like vectors at P. So meaning that it's is a the space-time is something like a manifold where each of the tangent space is like the the light cones, the forward light cones. So at each point you have, so you approximate the locally that you approximate the space-time locally by Minkowski spacetime. Okay, this is what's going to happen locally. At each point you have these forward light cones, which are the tangent spaces at each point of the manifold. Okay, so here is a more complete picture of the light cone structure, the figure of light cone structure of the tangent space on space-time. Okay, where M is space-time. So at each point, these time-like vectors are separated by from the space-like vectors here by the null vectors. These are null vectors. So this is the light cone. This is null. This is space-like, and these are time-like vectors. Okay. Alright, so at this point I think I'll take a break and we'll get back to you with the definition of proper time in the context of general relativity. Okay, thank you for attending this second segment.